All right, so now we're going to look at the high PO2 region and see what happens there. So we had already developed a relationship for this scenario. However, we had it where the oxygen went into an interstitial. And so, like I said before, oxygen tends to be the larger of the ions, and so that's not usually practical. So we're going to switch it up a little bit to make it more realistic in this example. So we have the gas on one side coming in to the lattice. And so instead of the interstitial sites, we're going to say that it goes to the oxygen sites. So this is more realistic. So we're going to essentially assume it takes one of those vacancy sites or something like that. And so coming in, we would, if this takes an oxygen site, then this should have a no change in charge. And so to kind of compensate or to see the effects that it would have with everything else, we have to consider what else would occur. And so in this case, we would have a vacancy on the metal site with a hole, with two holes to compensate for this. So this is the reaction that we're going to assume occurs for this. And again, there's variations, right, that we could do depending on the oxide that we have. You know, it could go to an interstitial, etc. But we're going to go with this for now and kind of see where this leads us. And so just like the other reaction, we can look at the Gibbs free energy, and we're going to call this oxide for oxidation, because the oxide is being oxidized. And so at this point, I want you to we have this reaction now, and we're going to go back to the slide for a second, and we're going to look at another quiz question. All right, so the quiz question I want you to look at is, we have just developed the defect reaction for the high PO2 region. And so you can go back and look at that if you need to. And I want you to write the mass action expression or the equilibrium constant for that scenario that we just discussed. So see if you can do that, and then we'll come back together and see what you have. All right, let's write the mass action now. So we're going to call this one K oxt for oxidation. And again, it's going to be products over the reactants. So in this case, we have OOX, the metal vacancies, and then P squared because of the 2 here. And on the denominator, we're going to have PO2 to the 1/2. So just like before, we're going to eventually get rid of this, right? Because this is going to be 1, and when we're left with this expression. And just like in the previous example, this is going to be equal to the exponential of minus delta G ox over KT. And similarly, this expression that we have also helps us understand the relationship between pressure and the vacancies, or excuse me, the metal vacancies, or the amount of holes, because we see that if we now increase the pressure, that this whole expression would go down, right? And so that means that we would also have to, that would also mean we have to increase the metal vacancies or the electron holes. So we can use that to kind of talk about the relationship between those two. All right, so we've talked about low and high. In the next module, we're going to go over the intermediate partial pressure.